At node 2, x is what? X is L. U is what? U is U2. So put it in this equation. X is L, U is U2. We find A2. So this is our A1, this is our A2. Put them back here for A1 and A2. We get this one. U1 and U2 minus U1. So factor U1 out. This is U1, U1. Factor it out. It would be 1 minus x over L. And this is U2 times x over L. These coefficients of U1 and U2, let's show them by N1 and N2. This is N1, N2. So N1 is 1 minus x over L, N2 is x over L. These are called shape functions. N1 and N2 are called shape functions. They are very important. These are building blocks of our solutions. They depend on this, and in this term, this course we are going to discuss and use this term many times in the future. So remember shape functions, N1 and N2. Now, this is the line element. This is a linear line element, very simple, the simplest type of element. Shape functions are 1 minus x over L, and N2 is x over L. This belongs to node 1, and this is associated with node 2. So U, this U, we can write it as N1 times U1 plus N2 times U2. This is what you see here. So displacement is written in terms of shape functions and nodal displacements. Well, in matrix form, we can write it. In this class, we like matrices. So because computers, we use computers, so computers work with matrices, with arrays of numbers. So U, we can write it like this. It is N1, N2, U1, U2. But now, these shape functions have some important properties. That's what we are interested in. A couple of properties. Let me see. Let's, first of all, N1, let me a little bit zoom out so you can see also the figure. I want to ask you a couple of questions. So are you ready? Tell me. Sure. Tell me. Look at this, N1 is equal to this. N1, and look at this node 1. At node 1, what is x? X is what?
0.
0. So what is the value of N1 at node 1?
1.
Very good. What is the value of N1 at node 2? At node 2, x is what?
L.
Very good. So N1 at node 2 would be?
0.
0. Very good. Let's look at N2. What is the value of N2 at node 2, at its own node? At node 2.
1.
1.
X is L, so it is 1. What is the value of N2 at node 1?
0.
0. So very good. So each shape function has a value of 1 at its own node, and it is 0 at the other node. So this is the property that we saw, that this N1 at its own node, at this node it is 1, and at the other node it is 0, and similarly this one. So each shape function has a value of 1 at its own node, and it is 0 at the other node. In addition, what is N1 plus N2?
Just 1.
1.
1.
They add up to 1. So sum of shape functions is 1. All right, so let's look at these properties of shape functions. Each shape function, this is what we discussed. Each shape function has a value of 1 at its own node, and it is 0 at the other. And the two shape functions sum to 1. If we plot them, the graph is like this actually for n1x. This is this equation, this is n1. Plot n1 versus x. It is this, n1 versus x. It varies like this. At node 1, where x is 0, it is 1, and it goes to 0 at the other node. It is linear variation. It's a simple type of element, so it varies linearly. N2, if you plot N2, this is N2. Just plot x over L, and this is this. When x is 0, it is 0, and then when x is L, it is 1. So N2 graph is like this. This is the behavior of these shape functions. These linear variations tell us that this is a simple type of element, actually. It varies linearly. Now, another property of this one, what type of equation is this? A1 plus A2x. This is a what function? Is it quadratic function? Is it cubic function? Is it linear function? What type of equation is this?
Linear.
Linear. Okay. What type of equation is this?
Linear.
Linear. The same as this one, linear. So shape functions are always of the same type as the approximation function. You start linear, you end up linear. You start cubic, you end up cubic. So the property shape functions are always polynomials of the same type as the original interpolation functions. And derivatives of linear shape functions with respect to x sum to 0. So derivatives that you can find, and they sum to 0. Let's now move on to trusses. That's what our main topic is today. This is one of the elements always in this class. Whenever you have questions, ask. All right, feel comfortable, feel free to ask. All right, you are not interrupting, and it is good to be active in your learning. I try to make it as active as I can, but I need you to be active. So always ask questions, participate. Now, this is one element. Trusses are simple structures. So we did it in, let's see how the formulations are done and what map did inside. This is one element of a truss. Node 1, node 2, length L. We define two coordinate systems. One coordinate system which is attached to this element. This is called local coordinate system. This is x prime, y prime. One is another coordinate system which is fixed, xy. It is fixed, it's not changing, it's fixed to the ground. So this is x prime, y prime. We call it local coordinate system. X, Y, we call it global coordinate system. Well, with x prime, y prime, there is a displacement u prime. U is always displacement in the x direction. So x direction, displacement u, y direction, displacement v. So u and v are displacements in the x and y. In the x prime and y prime, displacements are u prime and v prime, but it is not showing it here, but this is u prime and in the x prime direction and v prime in the x prime direction. But for one element, so this shows one element, x prime, y prime, it is local coordinate system, xy is the global coordinate system, this one. And angle theta, this theta, we always measure it from positive global to positive local, counterclockwise positive. So counterclockwise positive from global, positive global to positive local or elemental. This is the definition for our coordinate system. Now, we need coordinate transformation here because you see here we have two coordinate systems. One is this local, one is global. Then we find displacements in local. We need to find the displacements in global. So we need to do this transformation between these two coordinate systems. So let's see how these displacements transform from local to global or from global to local, vice versa. So here is what we need, transformation of these coordinates. This is our global xy. This is our local x prime, y prime. Displacement uv, u prime, v prime. And this is the angle theta. Now, from geometry, I have highlighted some of these points which are important to pay attention. This is our xy coordinate system. This is the global one. This is x prime, y prime, the local. This is attached to the element. And this is angle theta here. So if there is a displacement u and there is a displacement v, so this is u, v. So if we want to find the u prime and v prime, I want to, this is u and v, I want to see with respect to local, what is it? Well, I just draw perpendicular to this one. So this would be this side plus this side. It makes it u prime. In x prime, we have u prime. So this would be u prime. So u prime would be this piece from here to here, this, which is u cosine theta, this piece, u cosine theta, plus this. This is actually v sine theta here. This is this v sine theta. So what you see here is this one actually, u prime is u cosine theta plus v sine theta. This is similar to this one, v prime. If you want to find v prime, again, it is this side, which is negative u sine theta plus v cosine theta. So from the geometry, you can see it easily. Now, in matrix form, this u prime and v prime, we can write it like this. U prime, v prime is this cosine theta, sine theta, negative sine theta, cosine theta. This is this and uv. That's what we wanted. We did it. Primes, with prime means local. Without prime means global. With respect to global coordinate system. We related displacements in local to displacement global through this one. This is called transformation matrix. This is transforming them. All right, that is the transformation of these matrices. Let's now move on to element stiffness matrix in local coordinate system. I have highlighted this. In local coordinate system, we don't have any problems. We already have it actually, just as a repeating the same thing. This is, but in local, this is x prime, y prime. This is this bar, F1 x prime is force at node 1, displacement is u1 prime. At node 2, force is F2 x prime. Displacement associated with this force is u2 prime. Well, we know that we can write this F is equal to K delta L. This is, works like a spring, so it is AE over L u2 prime minus u1 prime. The same as in local coordinate system. With primes, we don't have any problems. F2x prime, it is equal to AE over L u2 prime minus u1. And at node 1, similar to this one, it is what we did here. Let me go back one step. This is what we did here, actually. We started today with this. But instead of this one, I'm just putting it at an angle. But with respect to its local coordinate system, so it is the same thing as what we derived here. So this is what you see here. This is what you see here. This is AE over L U1 prime minus U2 prime, and the same for F2. In matrix notation, we can write it like this. So this is the same. In local coordinate system, we derive this. It is F1 x prime, F2 x prime. This is our force vector. AE over L1 minus 1 minus 1, 1. This is our K prime. And this is D prime, displacement with respect to local coordinate system. So we can write it as F prime is equal to K prime, D prime. This is F prime, K prime, D prime. But everything is with prime. We don't want this. We want without prime. These are with respect to local, but we can't just follow the element. We have to find everything with respect to global coordinate system. So need to write in global coordinate system. We need to write it F is equal to KD without primes. That's what we are going to do here. So in global coordinate system, we want this F to look like this. You see F prime look like this here. F1 x prime, F2 x prime. But this is with local. Global, it should look like this. F is actually F1x, F2y, F1y, F2x, F2y. And the same displacement, there should, at node 1, there should be displacement U1, V1. And at node 2, there should be displacement U2, V2. So our F should look like this, and our D should look like this. Now, using the transformation matrix, we derive this one. This one, U prime V prime is equal to this. With displacement with prime is related to without prime, to global. Now, we need to expand this. We already did this displacement. We already did coordinate transformation. You see here, this is U prime, V prime. But we need to do this now for both nodes. It is U, V prime for one node, but now we can put it for the element for both nodes. So we can write it as U1 prime, V1 prime for node 1 and U2 prime, V2 prime for node 2. The same, put this cosine, sine, negative sine, cosine, this here and then here. This is this one. This is cosine, sine, negative sine, cosine. We put it for node 1 here and for node 2 here. This is our displacement vector. This is very important here, and this is our transformation matrix. What size is this? It is a
4x4.
4x4 matrix. Very good. This is the transformation matrix, and it is very important. It is will transform displacement in local and in global. Now, question for you. Forces are vectors or scalars?
Vectors.
Vectors. Vectors.
Vectors. You're right, because it needs these directions. Displacements are vectors or scalars?
Vectors.
Vectors. Why vectors?
They also need directions.
They also need directions. Very good. You're right. So so you can write this one D prime. This is our D prime is equal to this transformation matrix times D. This is D. That's what we wanted. Be related prime and without prime. This is for displacement. Well, forces are also vectors, the same. So they transform the same way. So is F prime is TD. If D prime is TD, the same, you can write it for F prime. F prime is also TF because they transform the same way. They are vectors. So our force vector, similar to this one, displacement, this forces, transformation matrix, and force vector without prime. They are related. All right, very good. So we have our, let's look at this one. We wanted this form. So we need to find this. F is equal to KD. We are good with this one now. We are good with this one. We related prime and without prime. We need this K now. This is a 4x1 matrix. This K need to be expanded here. You see, when we write our formula in this form with respect to local coordinate system with prime, f1x prime, f1y prime, f2x prime, f2y prime, and again displacement with prime. This is K prime in expanded form for the element now. So it should be like this: 1 minus 1, negative 1 here, and 1. Because now here, if you see f1x prime would be AE over L u1 prime minus u2 prime. That's correct. Now, if you look at f1y prime, it is AE over L. Everything is 0 here, 0, 0, 0, 0. So it would be 0. And f1y prime is 0 because there would not be a force in the y prime direction. This is a pull-push member. This is a pull-push member. There would be no force local y prime direction. So that is correct, the way that we expanded this, and the same for node 2. So we can write this as f prime. This is our f prime is equal to k prime. This is k prime times d prime. This is d prime. Now time to switch them to without primes. So replace f prime with tf. That's what we did here. This is f prime is tf. F prime is tf. That is this one. Substitute for this tf. This is k prime. D prime. Substitute again td. Multiply both sides by t inverse. By this t inverse, multiply both sides, it's t inverse tf, and t inverse times k prime td. This t inverse times t, it is what? It is identity matrix. Just remove it. So f is equal to t inverse k prime td. That is very good. We are very close to what we wanted to achieve. It's just one item here. You see, this T inverse is a question for us. We don't like to see this like this. Inverse of a matrix is always a little problematic for us. But the good news is that this transformation matrix is orthogonal, which means that its inverse is the same as its transpose. Remember, actually, in activity number 1, you showed that. Actually, in activity 1, actually, you showed that this matrix, remember, this matrix was orthogonal. You showed that its inverse is the same as its transpose. This property is called orthogonality. This matrix is orthogonal. Its inverse is the same as its transpose. You showed it in the lab. In activity 1, you did. The same is this one. The same is this expanded one is also the same thing. You see, it's the same thing actually here, and the same thing here. So its inverse is the same as its transpose. If this is the case, get rid of this T inverse, show it as T transpose times K prime T. That's it. So what we achieved, very important here, F is equal to something times D. That's we always want to see in finite element method. We always want to see F is equal to something times this displacement vector. This something is called element stiffness matrix in global coordinate system. That's what we wanted to find. Time to find it. if this K is equal to T transpose. We already know T. You know this T is here. This is T. This is our T. This is T. The same as this. This is T. Transpose of this one. T transpose times K prime. This is K prime. This is K prime. Times another T. Multiply this. This is T transpose. This is K prime. This is T. Multiply these three matrices. We get this one. That is what we wanted to derive. That is what FEMAP used when you solve truss problems. This is K. Element stiffness matrix for truss problems. This is for one element. We use this one for each of the elements in our truss problem, put them together, create the global stiffness matrix, and then solve for displacements. That's what we do all the time in finite element methods, to use this element stiffness matrix, and this is this one. Is it symmetric or not? This one is the same as this one. This one, the same as this one. Row 1, column 4, row 4, column 1, the same. This one, look at all of them. This one, this is the diagonal term here. This one, for example, it is what? Row 1, column 3, row 3, column 1, the same. This one, the same as this one. This one, so as this one, the same as this one. So this one, sine, cosine, this is this one. This is row 3, column 4. Row 4, column 3, the same as this one. So yes, it is symmetric, and symmetry always plays an important role in reducing the number of computations and memory. So that's it. That's what we wanted to find. Our force vector f1x, f1y, f2x, f2y is equal to k, is our k here that we found, k times displacement vector. F is equal to kd. That is what you see here, and that's what we wanted to achieve. We do apply it for each element, and when we put them together by global stiffness matrix, by direct stiffness procedure, or by superposition, and then create the global system of equations, and then apply boundary conditions and solve the problem. Solve for displacement, and then for post-processing, we can do anything we want. Our discussion took a little bit longer. Usually I try to make smaller lectures and then practice more in between, but this was longer because at the beginning, sometimes we have to spend more time. The next question is to find stress in each element. I don't want to discuss it right now because, as I said, I didn't talk too much. Let's practice. Time to solve an example problem. Then we will come back for stress. Remember, we are here to find stress, calculate stress. We will come back here, look at the formula, not a big deal. But then now let's solve this example problem and apply what we learned today. All right, questions before looking at this example problem? Any questions? Or are we ready to solve this problem? I think we are ready a little bit again. I had to talk a little bit too much, but we are ready to solve this problem. You have your paper and pencil ready? Calculator, paper, pencil. You are going to solve these pieces. I will ask you to do, and then you do this. When you apply this, you see what phi map did for us. It's a simple problem, but we go through this. We can apply the same technique for much bigger problems. For this problem, for the plane truss problem, determine the displacement of node 2. So this is our truss problem. Node 1, node 2, node 3. This is element 1, element 2. This angle theta. L is here. Modulus of elasticity, cross-sectional area length given. Determine the displacement of node 2. So this node 2. We want to find displacement load 10,000 pound, 10 kilopound applied here. Also determine the stress in element 1. We want to find the stress in this element, but we will go back and do this. Look at the formulation and complete this. So let's first find the displacement of node 2. Area, modulus of elasticity, length, we want to find this. First item is always to create the connectivity table. Connectivity table. So look at this one. Create the connectivity table. Let me see, I can show you. I have the camera to show you, but connectivity means from node I to node J. Look at this one, I, J, angle theta. These are the items I need. Node I, node J, angle theta. Element 1 goes from node 1 to 2. Theta is 45 degrees because our local is from 1 to 2 and this is global. So from global to positive local, this is 45 degrees. So the connectivity table, element 1, node 1 to 2 angle theta. Do this for element 2. Do this for element 2. Complete this connectivity table. All right, somebody tell me, what did you get for element 2?
From node 2 to node 3 at an angle of -45.
All right. Anyone agrees with your friend?
Yeah, that's what I got.
Okay, this from node 2 to 3 angle -45. Yes, because this is our positive global. And this is our local from 2 to 3. So put the coordinate system from node 2 to 3, this X prime. This X prime coming down here. So this angle, this is clockwise, makes it -45. Or what else instead of -45? What else can I use?
135.
Can I use 135? Anyone agrees with your friend or not?
Yeah, I think so.
Yeah.
No.
If you use 135, isn't it from 3 to 2? Like your reference changes.
Yes, you're right. You see what you said from node 2 to 3. Pay attention. From 2 to 3. So it's coming down here. So this angle is either -45, or if you want, you have to go counterclockwise, but you have to always connect from the positive global to positive local. So you can either say negative 45 or you can say plus 315 degrees, which is from positive global to positive local. So it would be plus 315 degrees. But you cannot say 135 degrees because you are saying from node 2 to 3. So X prime is pointing down. But as what your friend said, if you say from node 3 to 2, if you say from node 3 to 2, then yes, the angle would be positive 135 degrees. Everyone gets the point or not here?
Yeah, that makes sense.
Yeah, that makes sense.
Yeah, that makes sense.
All right, very good. Once we have the connectivity table, I want you to now use this one. This where is our stiffness matrix? This one is our stiffness matrix that FEMAP has it. FEMAP has this for many different types of elements. ANSYS, a very good, very comprehensive program. It has 100 different types of elements. So for each element, it knows which one to pick. So once you select the type of element, you remember when you selected element type, that's it. It takes this one. I want you to take this one like FEMAP did and apply it to element 1. Tell me, put the numbers here. FEMAP works with numbers. So use this one for element 1, AE over L, and these terms. Tell me what you get for element 1. First, tell me AE over L. This factor, keep it outside. 1 minute, put numbers, tell me what you get for AE over L, and then we go inside this matrix. This is the problem here. What did you get for AE over L? Anyone?
I got 10 to the 5th over root 2.
Anyone agrees with your friend?
Yeah.
All right, very good. You're right. Pay attention that this AE over L, this L is what? This L is not the same as this L. This L here is length of the element. This L here is just this distance. And we know also this is angle 45 degrees, so we can find this length of the element. So pay attention to this. If you do this, AE over L1, L1 is actually 100 divided by cosine theta, which is 100 square root of 2. So actually AE over L, this is AE divided by L, we get 10 to power 5 over square root of 2. So that is this factor. 2 minutes work on this, tell me what you get. I will check the numbers here with you. 2 minutes, find the element stiffness matrix for element 1. All right, I want to check with you, one of you. Tell me what you got for this first row. Give me the numbers for the first row.
1/2, 1/2, -1/2, -1/2.
Anyone agrees with your friend?
Yeah, I agree.
Yeah.
That's right, you're right, very good. This is what you get here actually for K1, half, half, negative, half, half. And with this, then that's it. Do the rest for K1, you find it like this. Do the same thing for element 2, that's what FEMAP did. You say they're negative 45 degrees or 315 degrees positive. And we get this one for element 2. Pay attention that degrees of freedom. You have to make sure these are addresses for our own purpose. Put these This is U2, V2, U3, V3, and U2, V2, U3, V3. This is for element 2. That is what we developed for element 1. For element 2, time to create the global stiffness matrix, we need the size of the global stiffness matrix. These programs, these are in C, C++, but in C or C++, we need to initialize. We need to know the dimensions of the matrix. We cannot, it's not like MATLAB. MATLAB is very good. You don't need to specify beforehand what the size of the matrix is. But with C or C++, we should initialize, we should determine the dimensions of the matrix. Tell me, what is the size of the global stiffness matrix? How many nodes do we have in this problem? How many nodes?
6 by 6.
It should be 6 by 6. Very good. How did you find it? Most likely like this one. How many nodes do we have in this problem? 3. How many degree of freedom per node? Each node has
2.
2 degree of freedom. You see that here always U1, V1, U2, V2. So each node has a displacement in the X direction and has a displacement in the Y direction. So 3 nodes, 2 degree of freedom per node makes it 6 by 6. So our global stiffness matrix should be 6 by 6. And that's what you see here. Number of nodes 3, degree of freedom per node 2. Therefore, 3 nodes times 2 degree of freedom per node, it is 6 degree of freedom problem. So that tells us what size of problem we are solving. For your information, of course, you know that nowadays we solve problems which are millions by millions, 10 million equations, 10 million unknowns. So the degree of freedom of the problem is 10 million. So we solve this by hand, so we see the procedure, but computers do not mind. Once we have the algorithm, the procedure, then they can do much bigger ones. This is the 6 by 6 global stiffness matrix, displacement vector, and force vector. Time to apply boundary conditions. At node 1, displacement in the X direction and Y direction are 0. At node 3, displacement in the X and Y are 0. These are homogeneous boundary conditions. Remove them from the system of equations. So U1, row 1, column 1 out. This is V1, this is V1. So row 2, column 2 out. The same thing for U3 and the same for V3. Row 5, column 5, and row 6, column 6 out. So we end up with now, so these U1, V1, U3, these are out. This F1X, F1Y, F3, these are out because we crossed them. We end up with F2X and F2Y. These are external forces. These are now boundary conditions. When you were applying boundary conditions at node 2, there is no this is node 2 external forces. No force in the X direction, just 10,000 pounds upward, positive. That's it. 10,000 pounds in the Y direction. This is 2 equations, 2 unknowns, solve for displacements, and they come out to be like this. So 2 equations, 2 unknowns here. U2 is 0, V2 is this one. And it makes sense because of symmetry. Node 2 doesn't have any displacement in the X direction. There is only one displacement in the Y direction, which is 0.141. That is the solution to this problem, part A of the problem. Any questions on this part before talking about stress? Now, let's go back to this stress. Remember, we didn't talk about stress. Time to look at the formulation for stress, and then we go back to that problem and then find the stress. So pay attention, you are going to do the stress. This is one of these elements. Node 1, node 2, this is our local coordinate system, and this is our global coordinate system. In local coordinate system, this is the formula we have. F1 x prime f2x prime. This is the local coordinate system. We had it AE over L, and these are displacement in local with prime. Everything is with prime. Now, if we want to find stress in this element, we need to divide f2x prime divided by cross-sectional area. This force by cross-sectional area. So f2x prime here is AE over L. Just take this out, this row out. So this is this one actually. So this is AE over L negative 1, 1. This is this one times displacement. But as you see here, so this f2x prime divided by area, if you bring this area down here, so sigma is f2x prime divided by area, E over L. But there is one problem here. These displacements are in what coordinate system, local or global? Anyone?
Local.
These are local. But displacement that we found here in this problem, displacement that we found here, they were in, these are the displacement that we found. They are in global. But this here, it is in local. Well, not a problem. We already know the transformation matrix. All we need is just to use this for U1 prime, U2 prime. If you do this, this is this one actually. This is T star. So this is just for taking this U1 prime, U2 prime out. It would be this times the displacement vector now in global. So we replace this one by this transformation matrix. This is a special type because it is just U1 prime, U2 prime are transformed. Times displacements now are in global. If we multiply it, we get this formula. Stress is given by this formula. E over L, negative cosine theta, negative sine theta, cosine theta, sine theta. This is the stress in each element. FEMAP used this for post-processing because now displacements are found. FEMAP uses this one simply to find stress. I want you to use this formula. Tell me what is the stress in element 1. So let's go back to our problem here. This is this one. I want you to use this formula. Tell me what is the stress in element 1. You have 2 minutes. Give me a number. 2 minutes. All right, anyone got the stress? Are you doing this or not? Anyone?
I'm still working.
Professor, I got 705 PSI.
705 PSI. Anyone agrees with your friend?
Yeah, I got that as well.
All right. Let's look at the here stress in element 1. We get this is E over L, length of the element. Remember, this is length of the element, and theta is 45 degrees, and U1, V1, U2, V2, plug them. U1, V1 is 0, it is pinned, and U2, 0, V2, we solve it here, U2 and V2. V2 goes here, 0.141. Just multiplying this, we get, it seems I have to zoom out a little bit. We get this 707 PSI, and it is in tension, and it makes sense. Next step, I would like you to do it for stress in element 2. It was not the answer as in the problem, just I want you to do it for element 2. 2 minutes, do it for element 2, plug the numbers, you see what you get. Just use numbers, not intuitive, whatever we should get or so, just use the numbers, see what numbers tell us.
I got the same thing.
You got the same thing. Anyone else?
The 705, right? That's what I got again.
You got again. Very good. You're right. Actually, for element 2, similarly, element 2, here, E over L, and now angle is negative 45, but here is the difference here. Element 2 goes from node 2 to 3. So these are displacements for node 2, U2x. This is U2, V2, and U3, V3 for node 3. So from node 2 to 3, that is the displacement vector for element 2. And plug the numbers, we get 707. That's what we expected to get. Yes, because from symmetry, you see both we got 707. This is 707, and we expect from even by looking at this, the geometry here, you see that these two from symmetry, they should have the same stress. Both of them are in tension, and 707, the same magnitude of stress. And displacement positive upward, no displacement in the x direction. So our result, the numbers that we got are correct. We solved this, used FEMAP and Nastran in the example problem actually that I showed you last Wednesday. I solved this problem, and all the numbers that we got here, we got it the same for displacement. I remember we checked also the same number we got exactly. So this is what FEMAP did inside, and we did it by hand, followed the same path and procedure. All right, any questions on this problem or whatever we discussed today?
For the quiz next week, we can assume to have problems similar to this.
Yes, it can be if it is, it covers everything. Our quiz on Monday next week, it covers everything. So the
Okay.
trusses will be included. That's right.
But it'll be handwork, right? Not like
By hand.
okay. Yeah.
Everything you do by hand and scan and then submit your report. What I see is what you write. So you have to show your work and write everything and always box your answer. All right, any questions?
For the lab activity that's due on Wednesday, you just wanted the plot and the 2 tables, right?
Whatever it is in the material to hand in for a grade. It says it very clearly, a graph of deformed and undeformed shape, I think it says, and 2 tables, 1 table for, I don't know, showing the forces or whatever, and then another table show this. So just follow whatever it is in the material to hand in for a grade. But I think
Thank you.
1 graph showing deformed and undeformed shape, but always superimpose deformed and undeformed. In most of these that in the handout, it tells you 1 graph for both of them superimpose, so we can see if the deformation makes sense or not. We have a reference when we can compare the deformed shape to undeformed shape, so we see whether this deformation makes sense or not. All right, now we have time. Let's a little move on. We talked about trusses, so that we don't have any discussions on that one. Let's now move on to talk about symmetry. Always look for symmetry in structures. They are aesthetically, they are better. They look better to a viewer when a structure is symmetric, and also in computations in finite element analysis, pay attention to this. It reduces the number of computations and also memory usage. Examples of this is this plate with a central hole. Look at this one. This is a plate and a central hole. Stress sigma we apply to pull this plate. Now, one item is to consider the whole plate in analysis. Another procedure is to use just 1/4 of this plate. There is no need to consider the whole plate in this analysis because this plate has symmetry about the x-axis and symmetry about the y-axis. So instead of considering the whole plate, we can just consider this 1/4 plate. This side, we are applying this stress here, sigma, so we keep the same stress. Now, this side that we are cutting and this side that we are cutting, we have to use appropriate boundary conditions. These nodes here along this side that we are cutting, these nodes are free to move in the x direction, but not in the y direction. So we put it on rollers. These rollers, their job is to apply this to move in the x direction, but to stop it from moving in the y direction. And the same thing here, when we cut this along this vertical line, these nodes here cannot move in the x direction. They can only move in the y direction because of Poisson's effect. When you pull this one, this will contract in the lateral direction. So these nodes will move vertically, not horizontally. So use rollers. The roller's job is to apply this to move vertical, but not horizontal. All right, so this is the use of symmetry. But
Professor?
now, yes.
So you see how you have stress pulling on the left and the right side.
Yes.
What if you took away the left side force and only applied it on the right side? Does that mean you could only use the top half of the plate, top or the bottom half?
You said instead of using the complete plate like this.
So like what axis of symmetry would you be able to apply if you removed one of the stress of the stresses that you're applying.
Oh, this side, if you want to remove, for example, stresses here, we can't do that because you see we are using this symmetry of the geometry. So if I consider, if I remove this stress here, then I'm not doing anything, then the whole geometry is here. I have to use symmetry in the geometry to reduce the size of the problem. So if I can do anything, I mean, if I, of course, for analysis purposes, I cannot use sigma here. If I apply stress here, I have to, let's say, put this on pin here, on a pin here and rollers here. So I have to apply boundary, change the boundary conditions, first of all, to analyze this full plate, but it is not using symmetry. In order to use symmetry, I have to use the symmetry in the structure, which is about the x-axis, about the y-axis, as what you see, a quarter of the plate. Did I answer your question, or you mean something?
No, I think that's good enough. I'm still learning, so.
Yeah, you have to, when we talk about symmetry, look at the geometry. This plate, geometry, not the loading. The loading is sigma, and sigma, actually, we cannot run it here like this. If you give this like this to FreeMap and Nastran, it will give you error, fatal error. It cannot run it because you cannot have load here. It needs displacement boundary conditions. It needs displacement. You have to constrain this. You have to constrain this. It's now free in space. It cannot do that in finite element analysis. We have to constrain this. So we have to, if you want to analyze this, we have to use a pin here and put all other nodes on roller. But this analysis involves the whole plate. We are not using symmetry, but the discussion is to use symmetry to do this. We are using symmetry. So symmetry refers to geometry. So use quarter of this plate. Now, another example is this one. This is a truss. We are applying a force of 2P here. It has cross-sectional area 2A and 2A here. Now, question for you. Is this truss symmetric about x-axis? This is x-axis, horizontal. Is it symmetric about x-axis? Yes or no, and why?
Yeah.
No, because of the load.
One of you said yes, and one said no because of load. Anything else? Is it symmetric about x-axis?
No.
No, why not?
I feel like the low 2P would change that downward. So then
Yeah,
the
you
top
see-
would be longer.
Right. Yeah, you see here what happens, although the geometry is symmetric, but if you apply a load 2P here, this node will, you are applying a force downward, so this node will come down. If this node comes down, so this node will come down. If this node comes down, so this member and this member, they will be in
Compression.
compression. They will be in compression. On the other hand, if this node comes down, this node also comes down, which makes this element and this element in tension. So as what you see from the loading point of view, if you apply this load here, these two members will be in compression, these two nodes will be in, these two elements will be in tension. this element will be in this element. If you apply a load here, so this element will be in tension, this element will be in compression. So as you see, the loading is not symmetric. So although geometry is symmetric, but loading is not. So response of this structure is not symmetric about x-axis, but it is symmetry about y-axis here. If you consider half of this structure, but remember this load 2p, half of this will be taken by the left side, half will be taken by the right side, and this area 2a and 2a we also need to divide to half. So yes, we can consider this vertical axis of symmetry, but apply P here, and this will be cross-sectional area, and these nodes will be on rollers. Allow this to move in the vertical direction, but do not allow this to move in the horizontal direction. So yes, instead of solving for the whole structure here, we can look at this, just half of this structure. All right, any questions about this? All right, no questions. So we finished our discussion on trusses and symmetry. There is another discussion here. I will not discuss this one, but just to give you a heads up for our next meeting, which would not be next week, but the week after, we will talk about axially loaded members, potential energy approach. A very powerful technique is variational method of infinite element formulations. We will look at this bar, which is subjected to generalized loading, body forces, traction, nodal forces. So we will look at this bar, but we look at the formulation of this problem by applying potential energy method, which is the variational method. And we derive very important formulas. In the previous derivation, it was by direct formulation, which is not very, which is the simplest form of infinite element method, but this gives us more information when we apply this technique. So that is what in our next lecture. On Wednesday, we will have our lab. Again, for the quiz, it would be next week. Make sure that you take the quiz on time. Right at 10 o'clock Canvas, you find the quiz under, again, here you go to modules and you see quizzes here. This is quiz 1, and then you click on this and you take the quiz, or you can click on this one, quizzes, and quiz 1 would be there. If you click on this, these are unnamed quizzes that I have to delete because I didn't do. These are nothing, so this is also nothing. So this, you see quiz 1, you click on this one and then you take the quiz. Again, I don't know, 30 minutes, 40 minutes, 50 minutes, you write it and download your solution on Canvas. It will stop at the right time, at the time that it is set. So do not exceed your time. Otherwise, it will not accept. This is about the quiz. On Wednesday, we are going to meet again for the lab. For the activity, we will solve a beam problem. Last time we used FEMAP to solve a truss problem. Wednesday, we are going to do a beam problem. All right, if no questions, everyone, I stop here. If you have questions, of course, you can see me during my office hours. Otherwise, have a good rest of the day. I will see all of you on Wednesday. Take care, everyone.
Thank you.
Thank